So hopefully you remember this. And what is relationship between MRC and question answering then? So I think I got this question a lot for students who just began studying this, studying NLP. And it's confusing because the two terms are very interchangeably used in the community. And I think some people also don't really care about the difference. But personally, I feel there is a critical difference in terms of how you think of it, rather than what the task is about. So MRC focuses on the machine's ability to understand text by asking questions, whereas question answering focuses on the machine's ability to answer questions. And you might think, what's the difference between these two? And there's a critical difference, actually, because it's whether you focus on the ability of the machine to understand or ability to answer. And from the product perspective, we don't really care about whether the AI at the back really understands my question or the document or not. What really matters to me is from user's point of view, whether you can answer questions correctly, right? So question answering is more of a point of view from the product perspective. It's more of a product related thing. Whereas MRC is more of a scientific thing, I would say, that you're trying to really test whether the machine that you created has the linguistic or language understanding ability. But it is true also that the question answering is one of the best tools to really test this machine reading comprehension ability. So that's why it's very oftentimes interchangeably used. And so, for instance, Stanford question answering data set, can we say it's MRC? Or should we say QA? I think you can say both. Either way is fine. It's an MRC if you want to really test if a model can understand document. But it's a QA if you want to use that model for your search engine or your product, whatever you create. So there is a slight but important difference. But in many cases, I think the people who use these two terms don't really think of the difference or want to emphasize the difference. Then what is open domain question answering? So in MRC or question answering, we're assuming that one document is given. In ODQA, the open domain means that there is no restriction on the domain. So maybe it's not the best term to describe it, but when we say open domain, then we mean that we don't want to be restricted to just one document, but we want to be looking at everything in the world. Of course, it's really hard to define everything in the world, especially if you're trying to formulate this as a, this problem in a constrained setting. Putting a problem in a constrained setting is very important because otherwise it's very hard to evaluate, right? So oftentimes, even if you say open domain QA, what it really means is that you're given a question and not just one document that you know that has the answer for the question, but the entire Wikipedia. If you're talking about English Wikipedia, you're talking about 5 million documents, and there are about 3.3 billion tokens, I think, as of something like 2019. So it's very large, but still it's constrained. So it's important that at least in scientific approaches for machine learning, we want to constrain things. In reality, if you're creating some product, then you might not want to just restrain on Wikipedia, because Wikipedia might not be comprehensive enough to contain every information that you want to access. So you might want to build your knowledge corpus not only from Wikipedia, but also some web documents, maybe some website that has a lot of medical documents. I think it's called WebMD for English, that contains a lot of medical related documents. You might also want to include some other kinds of wikis, not just Wikipedia. So that's why I also discussed what's the difference between the perspectives from scientific and more of engineering point of views. In scientific point of view, in many cases, I think the importance is that you constrain your evaluation environment. So it's not oftentimes the ideal thing to do if you really want to use that for products. So it's really important to really note that, because when you're reading papers, people will say, oh, they're using Wikipedia. So you might wonder, if it's open domain QA, why not use a lot more documents than just Wikipedia? And that's because you want to compare two models, apple to apple, with the same setting. At least same setting means that you're given the same questions, you're given the same knowledge corpus, and can you do better? Otherwise, it's really hard to know if your model is doing better because of more corpus or better model, etc. Right? So I want to emphasize that there is a just Wikipedia, because we want to compare models correctly. But even Wikipedia is very big. Told you this says 5 million documents, and of course it's increasing every day. More than 3 billion tokens. It's very large. As a comparison, each Wikipedia document usually contains a few thousand tokens at most. Very long documents might have more than 10,000 tokens. So you're talking about very large corpus, and apparently it's very not practical to just put this entire document to your machine reading comprehension model, because it's going to take forever to read everything in Wikipedia. So realistically, in order to approach ODQA problems, there are several approaches, but the dominant approach that has been there for a long time is that you somehow retrieve relevant documents. This is also called search. And I think many of you are familiar with what search is, because I think we are using that every day. If you go to Google, Naver, and then you search something, then you see a few documents that are relevant to your query. And that's exactly the same for humans, how they find answers to their questions, because they search and then they look into documents and then find the pinpoint the answers that they actually answer their questions. So same for the machines too. In many cases, the machine has to first search from a long list of documents, and then maybe one or maybe 5, 10. It doesn't have to be just one. Diagram I'm showing now is has searched just one, but you can basically get top K documents, and then you make your model to read those top K documents. K is usually 1, 5, 10, 50, 100, etc., but not larger than probably 100 in many cases. Then you might wonder, how does the document retrieval works? And so I'm not sure we're going to have enough time to really go over this in details. So I'll be very brief about it, and let me know if you have trouble understanding this concept. But I think many of you have taken the class, undergrad computer science class, and there's a concept called hashing. And what hashing does essentially is that you basically cluster similar things in the same bucket. So this is very similar to how you go to library and find your book. You cannot just go through every book in the library, which will be very inefficient. How you would do that is the librarians already have sorted the books in a way that similar books will be clustered. For instance, you will have history section, you will have some IT section, you will have science section. So then you can go into one of the sections that you're looking for, and then maybe in that section, now the books will be sorted in the alphabetical order, so that you can also easily find it. And this allows you to find your book very fast without going through everything in the library. And the same thing happens when you're trying to search a few documents from the entire web corpus or Wikipedia, that these documents are clustered. Similar documents are clustered together so that you can access to these documents very fast. But then this clustering, unlike how librarians would do, is not cannot be manually done, right? So what they do is that they try to map each document to vector space, and these vectors, similar vectors, are clustered together so that you can find your the closest vector really fast by just going through the clusters first. But that's the overall idea of document search. But it's actually not exactly true for every kind of document retrieval. For instance, in sparse document retrieval, it's a bit easier because in sparse vector, only few dimensions are active. So you just have to see which dimensions are active. And in this case, then clusters are easier to create. You just basically create the clusters by which dimensions are active among like 10,000, 100,000 dimensions. So that's why I'm saying it's not exactly the same for different kinds of retrieval, but I think that's a bit out of scope in this class. Hopefully, maybe in future semesters, I might try to include this or emphasize more on this. But for now, think of it as you have a lot of vectors on the left side. You have one vector that you're trying to find the closest vector from the left side. And then you can do this pretty efficiently with very not too much of approximation. So, and this is of course sublinear time. I mean, it's clearly not doable in linear time if you have like millions, billions of documents. So the first retrieval that we're going to talk about is sparse retrieval, which is basically word-based. So the idea here is that you're trying to find a document that has similar words to what the query has. Of course, the easiest way would be creating a bag of words. I think many of you know what that is. So bag of words is simply just you are creating a large vector where each dimension corresponds to each word in the vocab. And then, so you have a query, and then this basically has some words. So you're basically creating a very large corpus and a very large vector of 0, 1. And this corresponds to, for instance, whether the word Harry exists in the query. And this dimension corresponds to whether Ron, the word one, exists in the query, etc. Of course, then you will need one dimension for each word in the vocab. So you will need, if your vocab size is 10,000, then your vector will be 10,000 too. And it's very inefficient to store this vector as a dense vector. So you will need an efficient way of storing this. The most often time used way of storing this is called COO. So you're basically storing this as like dictionary, basically. So instead of storing like in dense vector, you store this like you just indicate which words, which dimension is hot. So in this case, index 0, 1, 2, 3, 4, 5, 6, 7, then you know that 4 and 8 is hot. So what you write is that instead of writing this as a dense vector, you say you have a word at 4 and you have a word at 8. Then by default, if you don't have the key in this dictionary, then you know that the corresponding word doesn't exist in the query or the document. You do this in the same way for documents too. Then you can just try to find the documents that contains the words in the query by just doing dot product between these two vectors. And it's very efficient to dot product sparse vectors. I think I'll leave that as an exercise, why this can be really efficient. But that's great, but then there's a few issues with this. And the biggest problem is that some words in English and also in other languages are very common, and you don't really care about whether you match those words in the document and query. For instance, the word is, or the word like, for instance, question mark, or the word, I don't know, what, the word in. These words are very common, right? And you don't really care whether both these words appear in the document that you're looking for, because these words don't really carry the important meaning in the query nor in the document. So the problem with bag of words approach, I think I did this BOW. The problem with the bag of words approach is that you cannot really distinguish between important and non-important words. Each word gets the same vote. That's a big problem, right? Because you just want to figure out documents that have a very same words as in the query, but also those words have high information, a lot of information about what you're looking for. So that's why we want to weight these different words differently, and that's the purpose of TF-IDF. TF-IDF stands for term frequency dash inverse document frequency. So we want to consider if each word is important or not, and also not just important to the document, but also is it important to the entire corpus. So TF corresponds to term frequency, which is basically indicating whether each word is important to the document. But IDF is therefore indicating whether each word is rare or important word. So rare words are important, by the way, from the information theory perspective too. Rare words, whether each word is rare or not from the entire document corpus perspective. That's why TF is computed only in the document. So you see this definition. So T is term. This is document. And F is frequency. So do you understand this equation? It's very easy, right? So this equation indicates that you want to count how many words, how many times a certain term occurs in this document or question. So TF-IDF is computed in the same way from the question and documents perspective, by the way. So you want to count how many times this term occurs in the document. That's FT, D. But you also want to count how many each term occurs in the document. So this is basically just, you can think of this as just number of tokens in document. So it's just basically how long the document is, the denominator in this equation is. And the frequency is just the frequency of how many times it occurs in the document. So then it's a ratio, it's less than 1, right? Because you cannot have more tokens of certain term than the everything in the document. But let's say if you have a document that has a lot of word fox, then this ratio will be high. So it's a very simple thing. It's basically, this TF is very similar to bag of words, depending on how you define bag of words. But in many cases, you define bag of words as the ratio of that word in that document, not just 0 and 1. So it's very similar to bag of words. But the IDF is very different. And IDF is not defined within the document. And this is a very important thing that you need to know. And I think a lot of students get confused. TF doesn't have the input, the uppercase D, because TF is independent of how other documents are. But IDF is always dependent on everything in the corpus. So during training, you will need the entire corpus to get the IDF of a certain document, or I mean a certain term. And again, this is not specific to documents. That's why we don't have D in the input. So TF-IDF, or of T and D and big, it's a small d and big D, is multiplication of TF and IDF, where TF only depends on T and small d, where IDF only depends on T and big D. Then how do you compute IDF? Remember that there is an important function in the beginning, which is log. What's the property of log? Log becomes 0 if this value becomes 1. So what that means is then, if we want to be careful when the whatever comes here is 1, then in that case the IDF will be 1, so TF-IDF score will be always 0, whatever TF is. Then what does this term mean? N is the number of documents, which is just equivalent to D is a set, so you can just say that N is equal to the cardinality of the big D. And then your denominator is counting how many documents have your target term. So you can see a trivial case where if your term appears in every document, then this denominator will be equal to n, which means n over n is 1, which means log of 1 is 0. So now you see why IDF is penalizing terms that are appearing a lot. If you have a term that appears in the every document, then you will have IDF of that term being 0. But if you have a term that only appears only once in like 100 documents, then you're computing log of 100. And here log is usually natural log, so it's not log of 10, base 10, but suppose it's log of 10. I mean, it doesn't really matter. It's really how you really define it. It's log of natural number because it's easier to compute from the computational perspective. But it doesn't really matter at the end, because the only difference is that you only have some constant to be multiplied if you're making this into log of 10 instead of log of natural number. But suppose it's log of 10, then I want to say that if this n equal 100 and then this only appears in one document, then log of 100 will be 2, so IDF will be 2. So then it means that it's really rare. So if it's non-zero and high number, then it means term is very rare in the big D. And it's very simple at the end. Now, the importance of a term to a document D, small d, relative to entire corpus big D is multiplication of the importance of term respective to that document multiplied by the importance of that term with respective to the entire document corpus. Very easy, right? So let's go over a quick example, TF-IDF example. I'm going to do a little bit of math. Just a second. Okay, so we're going to compute TF and IDF. Okay, so how do you compute TF? TF is just looking at, oh my bad. We want to compute TF here because TF is document specific. We want to compute IDF here. That way we can compute TF-IDF for each document, right? Okay. Oh, my bad. Sorry. So this doesn't work this way. What I was trying to say is IDF only depends on the term, so we can do this here, but TF depends on each document's frequency. So we have to do this way, right? And this is TF. Let's do TF first. So this document has 27 plus 3 plus 14 terms, right? So it's 30 plus 14, so it's 44 terms. But car appears 27 times. This will be 27 over 44. How about auto? Auto will be 3 over 44. Insurance is 0, and best is 14 over 44. But how about the IDF for each term? So we want to compute the IDF of car, and car appears in this case, in every document. So what happens if it appears every document? Then it's just simply 0, right? But actually, I want to say this. So yeah, so it appears in every document. So we are actually, there are several ways to define IDF. There are more complex ways to define IDF, but we are following the same definition from the previous slide. Car appears in every document, so car is simply 0. The IDF is. How about auto? It doesn't appear in 3, but appears in 2 and 1. So in this case, you're taking the log of, so it appears log of, what is it? You have n here at the top, so which is 3, and it appears in 2 documents. So log of 1.0, 1.5. In insurance, same thing. You appears in 2 and 3, but not 1. So it will be log of 3.2, and this will be also log of 3 over 2. Then you want to compute TF-IDF of a document. Then basically we just complete this matrix. I'm very bad table drawer. So we multiply this, the car's IDF to the car TF, which is 0. Actually, no. This is very bad of drawing, actually, my bad. So, and we want to actually now compute the TF-IDF, car, auto, insurance, and best. Then we want to multiply car 27 over 44 times zeros. This will be 0. And how about auto? Auto will be 3 over 44 times log of 3 over 2, which will be some number. Insurance will be some number too. And then insurance has 0 though, right? So this will be 0. This is some number, positive number. And this will be also some positive number, right? Then we want to make this vector 4-dimensional vector, right? This will be our TF-IDF of document 1. We can do the same thing for document 2, right? And then document 3. Then this will be the vector representations of these documents. And in order to compute the similarity between these, you can do cosine distance between these two vectors and try to find the, from the query's perspective, find the document that gives you the highest cosine similarity. That will be your most similar document to your question. So is it clear? Hopefully that's clear. Okay, so then now this really, we want to see how this was applied, how this was used in real NLP paper that now date back to 2017, right after the question answering, starting with the squad, has been quite popular in the community. So actually, now on, I'm gonna explain to you how the paper, how the model works by going through the paper. That's probably more comprehensive for you too. Okay. Okay, so this was written in 2017 from Stanford and Facebook. And I'm gonna just skip other things, but we're gonna go into this diagram that's probably very familiar with you. So as you see, it's exactly how the open domain QA worked initially, and still I think many state-of-the-arts are following the similar mechanisms, that you basically have a question, right? And then this goes into Wikipedia, and then you retrieve a document that's very similar to your question, and you put this into MRC model to get the answer, which is a span in the document. And you use some model to make this work. And that's it. Actually, there are not that many, a lot of details in the paper, so it's pretty easy read too. It's very easy to understand. So I actually encourage you to read it if you're interested. And the point here is that they used TF-IDF. So I'm going to point that to you. So I think they talk about TF-IDF. It's a hard time for me to remember. Okay, here we go. So you see that they don't really talk a lot about TF-IDF, but they mention it here, right? So they use TF-I weighted bag of words vectors, and they actually use n-gram features. So I want to briefly talk about what this is. We just talk about unigram TF-IDF by considering one word as our token, but it's also possible to consider each two words as a single token. So in that case, then your vocab size will be much larger. That's why also if you ever use TF-IDF by this Dr. QA model, you will see that your vocab is like not a few thousands, but then it will be multi-millions. And that's because even if your vocab is 30,000, unigram vocab is 30,000, if you're trying to implement bigram, then it will be at most square of that. Of course, you don't actually consider every bigram because many of bigrams will not appear in the training data, but still it's at most square of the unigram vocab. So note that in case you want to take a look into that. So I remember that this was something like 17 million, something like that, vocab sizes, which is unigram and bigram. I don't think they included trigram. But other than that, they're using exactly the same TF-IDF that we just discussed and applying that on the entire Wikipedia for fast retrieval. So I think that's pretty clear for most of you. And that's it. And they basically were one of the first to actually propose a neural net-based model for open domain question answering, and basically provide a pretty good baseline so that research can happen on top of these things. Yep. So I think that's it for this paper. So that's great, but I think we're going to talk about another way to retrieve documents after a really short break, which is dense retrieval. And this is, I want to say that quite different from sparse vectors because sparse vectors are token based, whereas the dense vectors, these vectors are actually existing in the arbitrary high dimensional vector space, right? So let's have a short 3-minute break and come back with for this dense retrieval and also discuss the paper that corresponds to this method. See you soon. We'll see you at 3:16 again. welcome back. Let's get started with the rest of the class. So we just covered sparse vectors, and as you see, the sparse vectors, each dimension corresponds to each token or each word in the vocab. So the benefit of sparse vector is that if you have common words between query and documents, then it's very hard to miss it because you have a dedicated dimension for that word. But the problem is that in sparse vectors, it's really difficult to encode syntactic or semantic information because you cannot really compare between words that are similar but different. For instance, you can say that excellent and good are different words but very similar in terms of what they intend to mean. But in sparse vector space, there is no way to compare between those two because they're just different words. But you might want to compare these words in many cases because you will see a query that's not exactly paraphrase, that's not exactly using the same words in the document, but semantically meaning the same thing. So that's why we want to oftentimes operate in dense vector space. And these are very good for capturing syntactic and semantic information. Although sometimes it's difficult to encode precise lexical information, but this is not too important as long as you retrieve top K, if any number of top K documents, because some documents might not be containing information, but you can just read all those retrieved documents and try to find the answer. So dense vectors allow you to really look into more, I'll say, documents that can be possibly similar. In some sense, that dense vectors have, I would say, high recall rates, where sparse vectors have probably higher precision rate. But because you're using retrieval for your downstream machine reading comprehension model, in many cases, achieving higher recall rate is more important than achieving precision if you're not too worried about the speed. So I think I'll briefly mention about the recent paper which you also use for your final project, which is called dense passage retrieval. You get why it's called dense passage retrieval because they're using dense retrieval for their open domain question answering instead of sparse. And I wanted to point out, because many of you might be wondering why this work, how does this work compared to the previous works? So I just want to point out that dense retrieval, although it seems to be pretty promising at this point. Back then, I think many people were not too sure if dense retrieval is enough to get good passages, because in questions like squad, you get highest recall rate if you use TF-IDF, highest retrieval accuracy if you use TF-IDF. But it turns out that, first of all, squad was not the best data set to test ODQA because of how the squad was created. But also, if you make your retrieval model very carefully, then it is possible to achieve very high retrieval accuracy, even just with the dense embedding, without any sparsity. So that's like one importance that this paper contribute towards the ODQA. This paper also doesn't have a lot of details, I think. I mean, what I'm saying is that it's very, of course, important work, but it's very easy read. So I also recommend you to read this. It's very easy. There's no really equation. I mean, just going through it, there are very few equations that are really about how you compute similarity, or this is about really how you compute loss, right? And other things are very straightforward and just go into experiments. So you see how the papers are really written these days, right? Very few equations, very different from probably the papers you read before 2017, because before 2017, people weren't using BERT or anything like that. They were creating their own model, so they had to actually do a lot of mathematical equations to propose or precisely describe their model. But nowadays, everyone's using BERT by default. So they just say we use BERT, but how we tune BERT is as follows. Of course, I mean, in this case, they use, I think, Roberta instead of BERT. But I mean, I'll say maybe they use BERT. Actually, I'm a bit confused. Yeah, I'm not sure which one, but you can think of this as very similar, Roberta and BERT. So you see that there are not a lot of information to go over from the high level. There are a lot of details, of course. But you will see that I wanted to show you this table. So you'll see that BM25 is very similar to TF-IDF, but a bit more advanced in a sense that it's a bit more complex equation. And BM25 achieves 59.1% of top 20 recall rate, whether the answer exists in top 20 documents or paragraphs. Whereas their proposed model achieves 79.4, which is like basically about 20% increase. So that's really big difference, right? But the funny thing is that the accuracy is the other way if you look at the squad. So NQ is natural questions, which is a question answering data set obtained from real user queries, real Google users. It actually was released by Google, whereas Squad was more of a artificially created from Turkers. And you will see that the BM25 accuracy is 68.8%, whereas DPR accuracy is 51.6. You can increase this by combining these two, BM25 and DPR, but just looking at DPR, it's now the other way, like negative 17%. So this is exactly the pros and cons of or comparison between sparse and dense vectors. Sparse vector allows you to never miss documents that exactly contain your query words. That's why BM25, which is similar to TF-IDF, sparse vector, achieves really high recall rate on squad, where a lot of words overlap between question and documents. And we see the DPR kind of struggles here. Dense passage retrieval struggles here. But natural questions, because they were obtained from real user queries, and then documents were found after looking into the user queries, there are not that many overlaps between question and the document. So we see that the DPR does better. And that was exactly the point of the paper, that if you want to use this for real queries, then we probably want to use DPR or dense passage, dense retrieval instead of sparse retrieval, which is, I'll say, not always the case. I mean, it's not exactly 100% always the case, because I also want to say that the modern search engines still are very heavily dependent on BIM25 or variants of BIM25. Naver, Google, they still use sparse vectors. So I don't want you to think that, oh, now everyone uses dense retrieval, no one uses sparse retrieval. That's not true. Sparse has a lot of advantages. One of them is precision, and the other is that it's really fast. So it's more of a research, especially NLP, that we are focusing much more on the dense part. But in reality, sparse part is also very important. So please do not think it's not being used anymore. But still, I think you get the point. So that's why we see that at the end, if we link this dense retrieval model with the question answering model or MRC model, we get a higher accuracy than the just using BM25. So probably the comparison you want to make is these two. So if you use BM25 with the question answering model, this is end-to-end accuracy, not the just the recall rate of top 20, top 50 documents. Then you see that the DPR using the same MRC model will achieve almost 9% improvement over BM25. But again, you see that the difference is the other way. You actually decrease your accuracy by 9% if you're testing on squad. So we clearly see difference between these two. And there are a lot of papers saying that, oh, NQ is much better than squad. But I personally think that that's not entirely true. There are some also benefits about squad compared to NQ. So I think it's important to take these words with some grain of salt. I mean, at least, I mean, I personally think that's not entirely true. Probably it's not the scope this probably class to really go into that, but I think there are some pros that Squad has relative to NQ2. Though NQ is more, natural questions more dominant in the community right now. Okay, so I think we went over the paper. So I put the link to the both papers we discussed today on the schedule of the class website. So if you're interested, please take a look. But that's it for at least. I mean, what I'm saying is that we're not gonna go further into the papers in today's class, but we're gonna move into the final projects. So we're gonna spend the rest of the class about how the final project will be outlined. So we just saw this dense passage retrieval model by it's called DPR, and we're gonna give you a DPR-based baseline code for the open domain question answering. And this was prepared by our TA, Miyoung. Thank you. And you're gonna start from here, and there are several directions you can think about. One of them is that you can try to improve the baseline's accuracy by proposing a new model, or maybe you're trying a new optimization approach, etc. You might also consider improving the baseline speed, or you might also want to consider minimizing the baseline's memory footprint, which was really important, or which was really the core part of the recent efficient QA challenge that I gave a link to in this slide. So take a look. And if you're interested in this direction, then maybe you might also want to participate in the future competition. And actually, in the competition, one of my students, Soy, was won one of the tracks. She got the best model. So it's also maybe good to talk to her if you're interested in this direction. And also you can try to analyze the pros and cons of dense versus sparse retrieval. That can be your project too. So I'll upload an instruction PDF tonight, which will be basically discussing these things with a bit more details. But without further ado, I'm gonna ask Miyoung to go over the DPR baseline code. So if you're here, please, I'll give you the I'll give you, I'm not sure how I can you actually present, Mio, or?
Yes.
Okay.
Can you give me the permission?
Okay, yeah.
I can share the slide.
I'll try to figure out how I can do that. Just a second. So we have 20 minutes. So I think you can go over the tutorial, and then we can have a very quick Q&A session. But of course, if you have more questions, please use GitHub discussions. Wait. Okay. Yeah, I'm not sure. Okay, here we go. Okay, I'll first stop this share, and then I'm gonna find. Okay, I think this is how I do. Young is here. Make. Oh. I'll make you co-host. Oh, ask to start. No, make co-host. Yeah. I made you co-host, so please start sharing your screen for the tutorial.
Okay, can you see my screen?
I can see you. Yep.
Yeah, then I can just briefly go through the baseline. This collab file is the DPR baseline using only the subset of Wikipedia, and this is also presented in Efficient QA Challenge baseline. And you can see the source in this page, and the baseline is also provided for the full documents and T5 models. So you can just experiment with this code. And because of the limitation of the disk or the RAM memory, I just load the pre-trained weights and predict the answers. You can train your own encoders and readers following the instruction in this DPR repository. And this is provided by the basebook. And it also provides the code for train your retriever, train your reader, and go through the inference. And so let's start the baseline. So this is the requirement. You just clone the DPR file and download some requirements file. And this is the start of the baseline. In this final project, we will use the open domain variant of the natural question datasets, and you can load this dataset using Hugging Face datasets package like this. So your data looks like this, just the answer and question, because this is the open domain setting. And your goal is to predict the answers when the question is given. And the upper one is the training data, and the lower one is the variance data, and the number of data is like this. You can also use the original natural question data set with the context is given for training your retriever. And yeah, we can load the data sets like this. And I think this is little tricky parts because this is the open domain question answering. You need a Wikipedia corpus to retrieve or search the relevant passages. And I only use the subset of the Wikipedia because subset of the Wikipedia is just 1 gigabyte, but the whole Wikipedia is 13 gigabyte. And when you download this 13 gigabyte on Collab, there's some problem happens. So I just use 1 gigabyte, and you can download this file with this link. And when you download this file, you can find your Wikipedia in this. Yes, this thing. This is the Wikipedia corpus that you can use for your retrieval. This data looks like this way, and the number of passages is this amount, and the example of your passages is like this. So when it is the dictionary and you can find your passage like this, it consists of the passage and its own title. And this part is loading your data for question answering and retrieval. Then you can load your DPR models by this code. You can download the pre-trained weight and pre-trained indexes with this code. Your download files can be found in these checkpoints and indexes. Checkpoints is for your model weights for reader and retriever, and the indexes is for your KAIST index, DPR index. KAIST is the package for fast search, like approximate search. And with this KAIST index, you can search efficient tree with your DPR dense embeddings. And because this efficient QA held last year, the model weight is a little old, so you can download the latest version of DPR weights for your final project. And the checkpoint and the Wikipedia embeddings can download with this link. Yes, you can find some instructions in this DPR repository. And I think I want to point out one thing is that I only use the subset Wikipedia because it takes only 5 to 6 gigabytes, but in your 5-minute project, you can use the whole Wikipedia, and whole Wikipedia takes about 60 gigabytes. But the performance is much better. This is the DPR full file, and this is the DPR subset file used in this baseline. And the performance gap is almost 6 to 7%. So it will be better to use DPR full file if you have enough disk uses or the RAM. this most of your these uses came from this DPR index. It takes very large file. It takes large disk and large RAM. And this is the arguments of this baseline. And the model file should be addressed. And you can also find your final prediction result file in this file. This code is for loading your encoder, and you just execute with this model file path, and you can easily load your encoder and reader. This is for the retriever relevant document, for the retriever part, for searching the relevant documents, but it takes almost more than 15 gigabytes RAM, so Colab have some problem if your Colab is the free version. So I just made this this retrieve JSON file earlier, so you can download it with this link. Just you can load this. Yeah. So after loading your models, you can retrieve your documents, and after retrieve your document, you just load the retrieve readers and train and inference your reader to predict the final answers for your questions. And because retriever takes a lot of memory and time, I pre-compute the readers, and you can download my readers with this link and just don't execute these cells. Yeah, this part. You can run these cells, but you can also download the readers only from this file path. And after download the retrieve JSON file, it contains the retrieved documents relevant to your questions, and the reader finally read these retrieved passages and predict the final answers and also validate the readers. And it takes quite a long time, about 40 to 15 minutes, and you can finally get the final EM scores for your model. And this score is almost 30%, and it is same as the baseline presented in the natural questions open data set. You can find the readers of this data sets here, and the baseline for this Colab is this, and our development data set is this efficient QA depth. So your baseline performance is 30%, as you can see here, this part. And when you use the full Wikipedia, you can get 37%. And when you use another models, you can get this amount of performance. So this baseline code just load your models and the index list that pre-computed, but you can train your own encoders and readers to improve your final project. I think that's it for the baseline. I'm sorry for my confusing explanation, but if you have any questions about the baseline, feel free to tell me.
One thing I wanted to actually thanks Bjorn, by the way. And one thing I wanted to actually mention that I forgot to mention in the announcements is that so probably now for your final project you might need more computations than Colab, even if you use Colab Pro. So I confirmed with Professor Jegel that Jegel showed that we can use some AWS credits. We have ample amount of AWS credits, so please let me know if you are in needs of AWS credits to do your final project. I'll give you instructions how you can request for that when I upload the PDF, which will also include the link to this baseline code. So please stay tuned for that PDF that will have all the information you will need for your final project. And please ask questions right now, or you can ask questions later in discussions. Okay, we'll wait for 1 or 2 minutes, 1 minute, and then if no one asks, then we're gonna actually end our class soon, sooner than 2:50, 3:50. Okay, so looks like everyone's okay for now. If you have a question, please put your question on GitHub discussions. So yep, so good luck with your final projects. So I think today's class is, that's it for today. And